Just a reminder, the test is on this Friday on 16/2 to 16/6. I did finish making up the test this weekend, and I can tell you that it is the type of problems that you have either on the take-home quiz or on the review set. Okay, so that's what you need to know how to do well on the test. Okay, all right. The homework I pushed back to Monday the 5th. That's the last day of class. So this is our last full week of class. Let's see. And again, remember that you can, for Friday, you can take an 8x11 front and back with whatever formulas, etc., and you'll be turning that in with the test. Yes? Is there going to be a review on Monday? Well, basically, remember, Mondays are only a 50-minute class. So how much reviewing we can do, we'll do. But, what? Can we start class early that day? No, I'm afraid we cannot start class early that day. Again, a reminder here about the final exam. There is not going to be any review sheet for the final exam. The final exam is going to be taken from the types of problems. All I'm going to be changing actually are numbers from the 4 tests, right? So my plan is to, I'll be grading the test over the weekend, so I'll be handing back to you the tests on Monday, test 4, and then, of course, I'll be posting the solutions for you guys. And then, of course, the solutions for the other tests are posted online. So, and again, for the final, you can bring with you and front and back 8x11. Okay. All right. So what we just started on a little bit on section 15.6, parametric surfaces and their areas. A parameterized surface, first of all, a surface is something that is two-dimensional, but a two-dimensional thing can be floating around in 3 dimensions. Okay, so it can have an x, y, and z coordinate. It can be parameterized like this as a vector function. The parameters are u and v, or that could be x and y or something else, but u and v. And so it's a function, x is a function of u and v times the I vector plus y, a function of u and v times the j vector plus z, a function of u and v times the k vector. And then u and v are ranging throughout some two-dimensional region that we're going to call capital D. We did a parameterization of one surface. I want to do one more before we get into the area topic. And so this example, find a parametric representation. That just means give me the parametric equations. A parametric representation of the surface z equals 2 times the square root of x squared plus y squared. Okay, and this is actually very simple. In fact, so simple you might not even see initially how to do it. Basically, we have 2 independent variables here, x and y, on the right-hand side. On the left side, we just have our z variable isolated by itself. So one way, there's actually 2 possible ways we could parameterize this. I'm going to show both of them. The first way is this. Okay, we need two parameters, right? Well, let x equal x, let y equal y. So that's a parameterization for x, that's a parameterization for y. Okay, x and y are our parameters, or our two parameters. And then z, well, we're given the formula for z, it's equal to 2 times the square root of x squared plus y squared. Okay. So we could represent, so to find a parametric representation, it could be r. Now this time it's not u and v, we've got two other letters of the alphabet, x and y. Okay. Now the first one is supposed to be the formula for x. Well, that's just x. X is equal to just x, so that's x times the I vector. Y is just equal to y, so y times the j vector. And then plus z, we have to put our formula here, 2 times the square root of x squared plus y squared. And then that's going to be times the k vector. Okay. So that's just one way of parameterizing it. Considering that the surface has an x squared plus a y squared in it, can you think of another possible way we could parameterize this with a different type of coordinate? Yeah. So a second way could be using polar coordinates. Or we could use polar coordinates. Okay, now with polar coordinates, let's see. Well, our x in polar coordinates is r times the cosine of theta, all right? Our y is r times the sine of theta. Now here, z is equal to 2 times the square root of x squared plus y squared, but we know that x squared plus y squared equals r squared. So z is equal to 2 times the square root of r squared, which I'm going to simplify as just 2 times r. Okay. So we have x, y, and z parameterized. Our parameters here are r and theta. Now, in this case, we have limits for the theta and the r. The theta would be going, now this thing goes all the way around, so the theta is going to go from 0 to 2 pi. And r here, well, r is going to be it's going to be anything bigger than 0, okay, because this thing goes out all the way. It doesn't stop. So r is just bigger than 0. And so we can represent then, let's get our function, our surface then would be r, that vector r. Now our parameters, though, are r comma theta rather than x comma y. And we just write our various functions here. X is going to be r cosine of theta, and that's times the I vector. And then plus y is r sine theta times the j vector. And then z we count is 2 times r, and that's times the k vector. And so we have another parameterization of this. All right. Okay. So we see how we can take a surface and use two variables, 2 parameters to represent this thing that's in 3-dimensional space. Okay, now what I want to go to next then, the next topic in this has to do with a tangent plane, and more specifically, calculating the equation of a tangent plane to a surface, we'll call the surface capital S. All right. Now, tangent planes, remember what tangent planes are. They're like giant cookie sheets that go 2 dimensions, infinity in both directions, okay? They're flat, they're 2-dimensional. Okay, so actually tangent planes are surfaces, 2-dimensional surfaces that exist in 3-dimensional space. Okay, so I'm going to give you the general reasoning here, and then we're going to do a specific example. Okay, let's say so actually here, let me show what I'm talking about here. I'll show this again. What we're looking at here is, okay, here we have 3 dimensions, x, y, z. And this gray area here, this is our surface that's floating around there. And what we're going to look at here is a particular point, we can call it P sub 0, that's on that surface. So it has an x, y, and z coordinate. And what we're going to look at here from this point is the fact that we've got 2 vectors that go in 2 directions. One is going in the direction of the u variable, the other one in the direction of the v variable. All right, and that's going to be how we're going to calculate this tangent plane equation. And I'll bring this back in just a moment here. All right, so we're going to suppose F, our surface, okay, I thought I heard something, is described by, okay, and we're just talking about that parameterization that we've just talked about. Some vector r of 2 parameters, u and v, equaling an x of u and v times I vector plus a y of u, v times the j vector plus a z of u, v times the k vector, all right? So that's our general surface. Now let P sub naught be a point on the surface S. So we're going to say that P sub naught is equal to the value when we put in u sub naught, v sub naught. So basically, let me go back here to this for a minute here. We have a particular point here. Over here in our 2-dimensional u and v plane that are our parameters, this particular u naught, v naught, that maps using our vector function to that particular point. Okay. Right. Okay. Now, at this point then, we have 2 tangent vectors. We have 2 tangent vectors, where one points in the u direction and the other points in the v direction. And the other points in the v direction. All right. Okay. And again, I had shown that we've got, there's our point. Here's, say, the one vector in the u direction. Here's the one in the v direction. And how we get these, those are tangent vectors. How we get them is just by taking the partial derivative first with respect to, say, u, and then with respect to v of our vector function. So let's call it the vector ru is one of these tangent vectors, and it's just the partial of x with respect to u. And I evaluate these at whatever u naught, v naught corresponds to our point that we're talking about. And that's multiplied times the I vector. And then we do the partial of the y function again with respect to u, And again, it's going to be evaluated at u naught v naught. That's times our j vector. And then finally, the partial of z with respect to u, again at u naught v naught. And that's our k times k vector. And we do the same thing for the r sub b tangent vector. So let me just get this down here. So this now, for this one now, we take the partial derivative with respect to v. So we have dx dd. And then we have dy dv times the j vector plus dz dv. And this should be evaluated at u naught v naught. Evaluated at u naught v naught. And that's times the k vector. All right. Okay. So we have these two tangent vectors. Again, let's put this up here. And these two tangent vectors are basically laying on the tangent plane that rests on the surface. So the tangent plane can be visualized like we've got this surface, this curved surface perhaps. We just lay like a cookie sheet on it. Just view it like that. It's a flat two-dimensional plane that sits right there on the surface, right there on that point. That's the tangent plane. All right, two-dimensional, flat. And these two vectors, the two from the partial derivative, are two vectors that are on that tangent plane. So the thing is, let's remember something. And what are we trying to get? We're trying to get the equation of this tangent plane. So let's take a little trip down memory lane here and recall something about tangent planes and their equations. All right. So recall. I know this is right there on the tip of your tongue. Let's say, let's call it n arrow. It's a vector. And let's say it has components number A, number B, and number C. Three components. And this is perpendicular to our tangent plane. So we've got some kind of tangent plane here, flat cookie sheet, and coming out from it, perpendicular, is this vector that we're just calling n. All right. Now, from this, we can get the equation of the tangent plane. We have, the equation is, the equation of the tangent plane is, we take the first number, a, that is multiplied by x, a times x, plus the second number b, b times plus by, plus the third number c times cz, and this is equal to d, some number d. Now, the only thing we have to figure out, then, we already have A, B, and C. We've got X, Y, Z. The only thing we have to figure out is what is the value of that number D on the right-hand side. And the way to figure that out is to just get one point that's on the plane, plug that in for X, Y, and Z, and we can calculate the D value. So we calculate D by plugging in the X, Y, Z values of a single point on the plane. All right. So that's something we had way back when, and let's then go and see how we can apply that to the present situation here. Okay, we've got these two vectors that are sitting on the tangent plane, so I can create a vector that is perpendicular to them by taking the cross product of the two vectors. All right, remember the cross product is a vector that's perpendicular to both of the given vectors. So, basically, the RU vector cross the RV vector is going to be perpendicular, that's a shorthand for perpendicular to the tangent plane. Okay. And then from this, we can get the equation of the tangent plane. And this we can get the equation of the tangent plane. All right, so let's look at an example here. Okay, so say we have a surface, capital F, and it's parameterized as follows. It's parameterized as x equal to u squared, y equal to v squared, z equaling u plus 2v. All right. Where u and v are real numbers, any real numbers. So where u comma v are any real numbers. Okay. All right, and of course what I'm really saying here is that the equation of f can be written like this. Vector r of uv is equal to, okay, the x function is u squared times the I vector. The y function is v squared times the j vector. The z function is u plus 2v times the k vector. Okay, that's just another way of saying. Okay, so so the question is find the equation of the tangent plane at the point on F of 1, 1, 3. Okay. So that's our point that we want to look at, that tangent plane that's sitting on that point. Now, first thing I want you to notice is that this point really is on the surface. Note 1, 1, 3 corresponds to u equaling 1 and v equaling 1. Okay, because remember, x is equal to u squared, so that's 1 squared is 1. Y is equal to v squared, so that's 1 squared is 1. Z is equal to u plus 2v, so that's 1 plus 2 times 1. So that is a point that is on our surface. All right. So what we have to do is we have to get these two vectors, RU and RV. Okay, so we do, for RU, we do the partial with respect to U. Let me put it in the bracket notation. So we go component by component. So U squared, the derivative with respect to U is 2U. The second component, V squared, that's a different variable, so it is 0 with respect to U. And then U plus 2V, that derivative is 1 when it's with respect to U. So that's our first vector, RU. Second vector, RV, I do the derivative across with respect to V. Now this time, U squared is the first component, so I get a 0. V squared is the second, so I'll get 2V. U plus 2V is the third, so I'll get a 2 there. All right. Okay. Now, we want to get or calculate the cross product, RU cross RV. Now, the easier way to do this is follows. Why don't right now, we know that U and V both equal 1. Why don't right now we just plug in those numbers so we don't even have to worry about the variables when we do the cross product, okay? So since U is 1 and B is 1, we know this, that our RU then is going to be 2 times U. That's going to be 2, 0, and 1. And our RV is going to be 0, 2 times 1 is 2, 2. And it'll be just that much faster getting the cross product. Okay. All right. So let's get that. Okay. So RU cross RV. And remember how we do this. We do I, J, and K. And then plug in our components 2, 0, and 1, 0, 2, and 2. And we do the determinant. Okay. So with the determinant, we're going to go across the first row. So we start with our I, and we've been through this just recently where we do then block out the row and column and get the determinant of the 2 by 2 matrix that we see, and that's going to be 0 times 2 minus 2 times 1. So that's a negative 2 for that part of it there. So that I got that as 0 times 2 minus 2 times 1. And then be careful, with the second component, you have to initially put it as a minus the J. So be sure you do that. And then we block out the first row and the second column, and what we have left there is 2, 1, 0, 2, and we get that 2 by 2 determinant, and that's going to be 2 times 2 minus 0, or 4. 2 times 2 minus 0 times 1. And then we have, we're back to a plus again, plus the K, block out the first row and third column. The 2 by 2 we have remaining is going to be, we've got 2 times 2 minus 0, so that's going to be another 4. All right, so let's see here. What does this come out to be? Our first component is minus 2. Don't forget about this minus sign. My second component is minus 4. And my third component is 4. All right. So this is perpendicular to our tangent plane. All right. So now we know therefore that minus 2 times x minus 4 times y plus 4 times z equals d. Some d is going to be our equation. We now have to find d. And of course, we're told the point that we're dealing with. The point is 1, 1, 3. So I plug in the x, y, and z values. Okay. So I get minus 2 times 1, minus 4 times 1, plus 4 times 3 equals d. And I think that comes out to 12 minus 6, right? So d is equal to 6. So our final answer then is this, minus 2x minus 4y plus 4z equal to 6. And if I'd like, I noticed that those are all even coefficients. I could divide everything by 2 and have the equivalent equation. So I could have 4 minus x minus 2y plus 2z equal to 3. All right. Okay. So you have one of these on, I think you might have one on the quiz. I know there's something on the review section about it, so you want to be sure that you're up to par with doing a problem like this. I need to do something here for a second. Let me just re-copy this stuff. Annalie, I'm just recopying all this stuff that I had written initially. Okay. All right. So this is just about the coming week and all that. All right. Then the other thing then in this section has to do with calculating surface area. And actually, in this, we have, we actually have two cases that we're going to look at here. Two cases. And and I don't know, we'll see how far we get with this because it's Monday. Here's the first case. Okay, so we're trying to figure out a certain surface area. So we've got a surface floating around. Somehow we've limited off a certain part of it, and we want to find out what's the area of that surface that we're looking at. So the first case is our surface is given as a parameterization. Our surface is given as a parameterization, which is what we've just been talking about. R of some vector function R of uv equaling x of uv times vector I plus y of uv times the vector j plus z of uv times the vector k. Okay. Now, we're going to assume that u and v are varying through a region, through a 2D region that we call D. Okay, so they're going through various values through this region D. And let F be the surface generated, be the above surface generated. And one thing we want to make sure of is that we only go through F one time. Somehow we've got to be careful that as u and v are going through this region, we're not going through F and then as if repaving it over again. Okay, that we're only going over F one time. So we're going to assume that the surface area generated and F is covered just one time. Just one layer of paint, so to speak. Okay. All right. Then here's the formula here. Put an asterisk by this. The surface area of S, we're going to denote it as capital A of S for area, is given by this formula. The double integral over our domain D, capital D, of the magnitude of the cross product of those two tangent vectors. So let me kind of put in English what this is right here inside that integral. We're taking the cross product, it's the magnitude of the cross product of RU and RV. And we know that by magnitude, that means, it's the square root of the squares of each of the components, right? Okay. All right. Oh, my. Okay. All right, I think this is what we'll do. For a couple of examples here, I don't think we have enough time to do it. I'll be rushing through. So, what we'll do here then, start on Wednesday, we're going to go through an example of this case We're going to look at the other case, which is actually simpler, and then that'll be the end of this section. And then we'll see, bring your review with you, then because we have 2 hours on Wednesday, and we'll go through some review questions. I might also take questions on the take-home quiz also as a possibility. However, I will not work the entire take-home quiz for you. I don't know. So anyway, we'll see you on Wednesday then.
I'm sorry.
Does it hurt when you talk? No? It sounds painful. When did it start? When did it start? Friday or Saturday? Okay. Oh, wait a minute. Wait a minute, Tom. I will not be attending class on Wednesday because I'm going to be at senior. Oh, that sounds like fun, Annalie. So what I tell you to do, of course, is watch the video and look at the notes that I post online. Okay, and that goes for anybody else who is going to the senior trip. Okay, thanks.
I understand I can't, but I have a homework in class, last class, and actually forgot to turn it in.
Oh, I haven't. Yeah, wait. Let me stop recording.